This is Lab 3 Circuit Design by Quentin Lumsden. So brief introduction. So the purpose of this lab was to predict the behavior of currents of circuits with resistors in series and in parallel using calculations and then experimental values using a simulator. And just generally measure the values of conventional current and potential differences and examine the behavior of ohmic resistors and capacitors. So results, the calculations were generally aligned very closely with the observed values, and the total potential difference is 0. So a few key concepts is the loop rule, which is just that across any loop in a circuit, delta V will equal 0. Node rule, In is equal to I out, and Ohm's law, that the delta V across resistor is equal to the current times resistance. So here's the conventional current predictions. So by taking the V total and dividing it by the total resistance, we can get the current across the whole thing because everything is in series. And noticeably, I only have one value calculated here, 0.0204, which aligns very closely with the current measured at both I1 and I2. So why are these the same? Why is I2 equal to I3? They're equal because when everything is in series, current is constant. If something was in parallel, there might be a different resistance somewhere along the circuit, but since everything is in series, it is the same, it's constant. And if you were to insert an emitter the other way, the current would likely be negative. Would be negative as it was going at the negative node. However, the magnitude would stay the same. Next, we checked voltage. So we removed an emitter and then put a voltmeter in its place. And the potential difference reads 3 volts across the net created gap, which is the difference between the which is the total voltage of the batteries. So, but the emitter is now 0. Why has that happened? So the emitter is removed. The circuit is broken due to the high resistance of the air / the voltmeter, and in order for the emitter to make a reading, there must be some kind of current flowing because it's measuring current, obviously. However, the voltmeter measures potential difference, which doesn't require current to work. And so it does read a number because it needs no current. However, the emitter does. So here's the potential versus position graph. And as can be seen here, there is large jumps of potential difference across the batteries and whenever there is a resistor. However, across wires, there is no potential difference, no measured potential difference. So when we touch the voltmeter, we should be altering the circuit, but why does the emitter reading change? So this is because the resistance is so high in the voltmeter that it draws incredibly little current, functionally not changing anything. Theoretically, it does change something, but not measurable. And if I believe we're working with an ideal voltmeter, in which case the R is 0. So now putting the resistance in parallel. So when we place in parallel, as you can see here, the current now changes. This is because the circuit is now affected in a different way, and because the resistance across the emitter is 0, no resistance or no current will flow through the 100 ohm resistor. So functionally, this drops the overall resistance to 47 instead of 147. So this obviously changes the current. And here are just the calculations for the current. As can be seen, that the resistances for the for the resistors lines up with the calculated values based off. That should be a 0.02. Apologies. Based off the currents also calculated, and the wires are both found to be 0, and our emitter is found to be 0 with the potential difference, with the 0 resistance. And so now looking at the circuit, the RC circuit. So as you observe the light produced by the 10 ohm ball, what happens to the light is so it immediately lights up, but then fades as the capacitor charges. Then when we can disconnect what then happens to the light, we can see it's actually the same thing happens again as the capacitor discharges, it releases charge and it lights up for a while, and then eventually the charge and the capacitor reaches zero, and then it fades. So when you first complete the circuit, what happens to the current? I should add there. So the current decreases over time as the capacitor charges, and the same thing happens when you remove the circuit from remove the circuit. Current then again decreases over time. However, it should be noted in both these cases, in both the current flows in opposite directions as you discharge it versus charge it. So is just the discharge and charge time. Charge time was about 2.3, measured to be about 2.3 seconds, and discharge time was measured to be about 2.26 seconds. And for the 20 ohm bulb, it was 5.87 seconds, and discharge time was about 5.33 seconds. So as you can see, when there's more resistance, it takes longer to charge, and discharge and charge time are equal. So here is measuring the RC circuits over time. As the voltmeter discharges, what is the voltage and the change in voltage? So specifically, we're measuring change in voltage. Over here we can see the actual numbers, the voltage in this, the delta V, and then the delta V over dV total. Its dV total is 9. And so this is the numbers. The slope of a negative 1.89. However, this was largely thrown off because of this first number with a large outlier here. So as we can see, the next experimental was calculated slightly differently. So predicted, we simply times the resistance times the capacitance, which is 30 ohms times 0.2, which is about 6 seconds. However, so that's the expected time for it to take. However, in the experimental, so the voltage at 20 seconds was 0.32, as we see here. We take that and divide it by 9 for the delta V. That gives us 0.356, and that should be equal to e to the negative 20 over RC. So that we take the ln of that, giving us negative 3.34. We then divide negative 20 by negative 3.34, and we get about 5.99. So as you can see here, the experimental calculated values line up very closely. So as far as errors and conclusions, so no significant differences between equations were calculated. It seemed to be fairly similar across the board, which is to be expected. And sources of error, timer error likely could be inconsistent or wrong. However, this is hard to eliminate without a more computerized procedure. So a few what ifs. So what if you were doing this lab in real life and used an actual meter instead of an ideal one? What would be the difference and how would it change everything? So an ideal emitter has zero resistance, but in reality, real emitters have some kind of resistance. So current would change. They'd functionally act like a very, very small resistor. And then same kind of idea. If you were to charge up a real capacitor with no resistor in the circuit, so in theory, in an ideal model, it would charge instantly because there's no resistance. However, in reality, wires have resistance, and so there would be some kind of resistance. And because there's some kind of resistance, it will not charge up instantly. Thank you, and I'm sorry for how long this went.